Hi everybody. So in today's video, we are going to be going through lessons 2 from unit 7, which is all about solving differential equations using a technique called separation of variables. Now, let's start by going over the learning target. So our learning target for today is that we are going to use the process of separation of variables in order to solve a differential equation. Now, this is very similar to what we did in the previous lesson, where we were solving a differential equation, which means that what we're trying to do in this lesson is we're still trying to find the original equation by looking at the derivative. The only difference is the technique that we're going to use today. And the reason we're going to have to use a different technique today is because the setup of the problems that we're looking at is going to be a little bit different than the types of problems we were looking at last time. So this idea of separating the variables is the name of the strategy, the technique that we're using, but it's still the same goal of finding that original equation by looking at the derivative. So let's go ahead and get started. And we want to start today with a little bit of a review. So what I want to review is finding the derivative of an equation that looks like this. E to the y equals 3x squared minus 2. Now, if you think way back to something we did a long time ago, we said when you want to find the derivative of an equation where y is not alone, there's a special rule we have to follow. So step number 1 is to take the derivative. So the derivative of e to the something is just e to the something. So the derivative of e to the y is e to the y. But whenever we see a y, we need to multiply that derivative by dy over dx. And essentially what we're doing there is the chain rule. Whenever your input, your inside of a function is not just x, you need to multiply by the derivative of the inside. But to represent the derivative of y, we just write dy over dx to do that. Now this is going to be equal to the derivative of 3x squared, which is 6x, and then the derivative of negative 2 would just be 0. After we found that derivative, our next step was just to get the dy over dx by itself. So in order to do that in this problem, my next step would be to divide by e to the y on both sides of this equation. Now, once I do that, I get dy over dx equals 6x divided by e to the y, and that would be my derivative. Now today, using the technique of separation of variables, we are going to be undoing this process. So the idea here is, just like there's a special rule for doing the derivative when your y is not alone, there is a special technique or strategy for doing the antiderivative when your y is not alone. Let's take a look at an example. So the strategy we're going to use today has 5 steps. The last step, the solving for y, which is the last step here, is typically the most challenging step because it requires us to remember a lot of algebra that we learned a long time ago and we may be a little bit rusty on. So as we go through these examples, keep that in mind. The first 4 steps here are really the kind of new thing. The 5th step, where you're solving for y, is a review of a lot of algebra that you've learned before, but it is going to require some practice to remember all those different algebraic strategies. So step number 1 in the separation of variables technique or strategy is to start by separating the variables. Now, here's how we're going to know we need to do that. If you look at this equation right here, and you can see in this equation, the y and the x, the y is not alone. The y is actually inside of the equation here. So whenever y is not alone, your first step is to separate the parts of the equation that have a y in it from the parts of the equation that have an x in it. Now, here are the parts that have a y. We have a dy here, and we have an e to the y here. Here are the parts that have an x. We have an 6x here and a dx here. In order to separate these, to get all of the stuff that has a y, or the stuff that I've highlighted in pink on the left-hand side, and the stuff that I've highlighted in orange, all the x stuff on the right-hand side, we're going to just use algebra to do that. So in order to get that to happen, I'm going to start by multiplying by e to the y on both sides and multiplying by dx on both sides at the same time. So step number 1 is you want the y on the left and you want the x on the right. And to do that, I'm just going to multiply. So when I multiply here, if I multiply by e to the y on both sides, and at the same time, I multiply by dx on both sides, so I'm kind of doing two things at once, what I end up getting is this. The e to the y cancels on the right-hand side, and on the left-hand side, I'm going to have e to the y times dy. Now, on the other side of the equation, the dx cancels on this side, so I just have 6x times dx on the right-hand side. So by doing this, I have separated the y's and the x's. Now, step number 2 is to integrate both sides. You might be wondering, why are we integrating on both sides here? Well, what we've learned is that integrals are the opposites of derivatives. They're inverse operations. So by integrating on both sides, what we're really doing is we're undoing this dy and we're undoing this dx, which means the derivative of x. So if we know that this is the derivative of y and the derivative of x, step number 2 is integrate in order to do the antiderivative, or in other words, undo the derivative. Now, the antiderivative of e to the y would just be e to the y, because the antiderivative of e to the something is always just e to the something. And the antiderivative of 6x would just be 3x squared. Now, if you think back to when we first learned about antiderivatives, you'll remember that we need to put a plus c. But we're going to write a plus c on one side only, and that's because even if there was a constant on both sides, eventually when you solve, you end up with constant only being on one side. So to save us that work, we're just going to make a rule that we're going to put the plus c on one side only. That right there is the only calculus part of the whole problem. After this, I like to think about the next few steps as sort of just algebraing. So the next step is going to be to solve to figure out c. Now that should sound familiar. In the previous lesson, we learned that after you do the antiderivative, you plug in your initial value to figure out what your c value should have been. So I'm going to go ahead and take this initial value right here, f of 1 is equal to 0, and I'm going to go ahead and plug in the 1 and the 0 for the x and the y. So I'm going to have e to the power of the y is 0 equals 3 times the x value that I'm plugging in, which is 1 squared, plus c. Now, e to the 0 is just 1. 3 times 1 squared is 3 plus c. And so if I subtract, I figure out that c is negative 2. So that step right here is the solving for c. Once you know c, you can go back and plug it back in. And so my new equation that includes the c value, which is negative 2, would be e to the y equals 3x squared minus 2. The last step of this problem, and as I said earlier, this usually tends to be the most challenging step because it does require us to review a lot of the algebra that we learned earlier in our mathematical career, is to solve for y. So in order to solve for y here, which means I want to get y by itself, I'm going to go ahead and start to use some of those algebra skills to get y alone. So step number 1 is to undo e, the inverse operation, be the natural log. So I'm going to go ahead and do the natural log of both sides of this equation. The natural log and e cancels, so I just get y equals the natural log of 3x squared minus 2. And in this case, that would be my final answer because y is now by itself. Okay, let's just recap. The new step, the only thing that's different from what we did in the previous lesson is that first we need to separate the variables before we integrate or do the antiderivative on both sides of the equation. After that, we still find our c value and we still get y by itself. And that requires a little bit of our algebra skills that we may need to review from previous units of math. Let's go ahead and try a few more examples. Now, we're going to do several examples here because there are lots of little algebraic things that come up in the course of these examples that I think it's important to review because, again, we might be a little bit rusty on some of this stuff. So please bear with me. This is going to be a few examples in a row just to make sure we cover some of that algebraic stuff. For this problem, it says, suppose dy over dx equals 3xy, find the general solution of the differential equation, then find the particular solution if f of 2 is equal to 1. The first thing I want you guys to notice is that in this problem, the y is not alone. So because of that, it tells me I need to use my separation of variables technique to get the y and the x separated. Now, I'm going to copy down my equation. It makes it easier for me to show my work and organize my thinking if I have an equation where I can actually do the work underneath it. So the idea here is I want to get the y on the left-hand side, or all the y stuff, and I want to get all the x stuff on the right-hand side. In order to make that happen, I'm going to do two things at once. The first thing is I'm going to go ahead and multiply by dx on both sides. Now, that's going to cancel on the left, and it's going to not cancel anything on the right. I'm also going to, at the same time, divide by y on both sides. Now that's going to cancel the y on the left, and it's going to make me have 1 over y on the right. So my new separated equation would be 1 over y times dy. And I'm going to have 3x times dx. So by doing that, I have separated the y's on the left-hand side and the x's on the right-hand side. Now, when I see a problem that has a fraction or a division problem like this, I have to sneeze. I'm so sorry. If I see a problem like this, I like to usually rewrite that as y to the negative 1 power. If you think back to all the rules that we've learned about antiderivatives, that should kind of jog your memory as a special case. Now, this dy and this dx mean that this is the derivative and this is the derivative. To undo a derivative, we do the antiderivative. And in order to do that, we just sort of integrate or do the integral on both sides. Now, once I do this, I'm going to have, because this is y to the negative 1, the antiderivative is going to be the natural log of the absolute value of y. And on the right-hand side, if I do the antiderivative of 3x, I'm going to have x squared, and then I'm going to divide by that new power. So I'm going to have 3 over 2, and then I'm going to have my plus c. Now you'll notice I'm only putting the plus c on one side. I'm not putting the plus c on the other side because eventually when we were solving to get y by itself, all of those numbers would end up together anyway. So we only need it on one side. Once I have that value, I'm going to go ahead and plug in the initial value that I was given in the instructions here. F of 2 is equal to 1. So in my equation, I'm going to go ahead and plug in 2 for the x and 1 for the y. So I'm going to have the natural log of the absolute value of 1 equals 3 over 2 times 2 squared plus c. Now, the natural log of 1 is just 0. 3 over 2 times 4, because 2 squared is 4, would just give me 6. Which means when I solve this, I get c equals negative 6. And I'm going to go ahead and take that c value and plug it back into this equation. So my new equation is going to be the natural log of the absolute value of y is equal to 3 over 2 x squared minus 6. Now, the last step of my problem here is going to be to use algebra to get y by itself. So what I'm going to do here is I'm going to use e to undo natural log. Just like natural log undoes e undoes natural log. So I'm going to do e to the power of the left side and e to the power of the right side. Now this natural log and the e are inverse operations. They basically cancel each other out. So we get the absolute value of y equals e to the 3 over 2 x squared minus 6 power. And that is all part of the power of e here. Now, in order to do an absolute value, we need to remember that absolute values have two answers. So when I want to get rid of that absolute value, I need to put a plus or a minus over here on the right-hand side. And now we need to do one last step. In your final answer, you are never going to have both a plus and a minus. You need to decide, should I keep the plus or keep the minus? The way you decide whether to keep the plus or keep the minus is that we use the initial value. If you plug in the number 2 for x here, you have 3 over 2 times 2 squared. Now 2 squared is 4, so 3 over 2 times 4 is 6, and 6 minus 6 is 0. That means you're either going to have positive or negative e to the 0. Now because the y value was supposed to be positive 1, and e to the 0 is 1, you want to keep the positive because you wanted your answer to be positive 1. That's what the initial value tells you. You want the answer when you plug in the number 2 to give you positive 1, not negative 1, positive 1. So in this case, we make the decision that instead of keeping both the plus and the minus, we're just going to keep the plus. So 3 over 2 x squared minus 6, and that is my final answer. Your final answer should never have both a plus and a minus. You should always keep one or the other depending on what the initial value tells you you're supposed to have. And the way you make that decision is just plug in the x and then choose the plus or the minus based on the y you want as your outcome. All right, let's take a look at another example. Like I said, every example has a few little tricky algebraic things in it. I just want to make sure we have a chance to talk about all those things before you try some problems on your own. So for this example, again, I'm going to copy down the original problem. Now you'll notice that again in this example, the y is not by itself. So just like when we took the derivative, we had a special strategy. When we do the antiderivative, we're going to have a special strategy. In order to find the solution to the differential equation, we're going to need to separate the x's and the y's here. So in order to move all of the y stuff to the left-hand side, I'm going to start in this problem by multiplying by y on both sides. And that's going to cancel the y on the right. I'm also going to multiply by dx on both sides, and that's going to cancel the dx on the left. So what's left over, now what I have now on the left-hand side, is I have the y that I just multiplied by, and I have the dy that was already there. And on the right-hand side, I have the x squared that was already there, and then I have the dx that I just multiplied by. Now again, I want to remind you that dy and dx means this is the derivative. So to undo derivative, we do an antiderivative, or in other words, we like to say that we integrate, which is the inverse operation of derivatives on both sides. The antiderivative of y would be y squared, and we have to divide by that new power, so 1/2 y squared. And on the right-hand side, we would have x cubed, and we would have to divide by that new power, so 1/3 plus c. At this point, I'm going to sort of take a detour, and I'm going to take that initial value that I was given in the original problem, f of 1 is equal to -1, and I'm going to plug in x is 1 and y is -1 to find the missing value of c. So if I plug that in, I'm going to have 1/2 times -1 squared equals 1/3 times 1 cubed plus c. Now, -1 squared is just 1, so you have a half. There we go. Select the right color. 1/2 equals 1 cubed is just 1, so it's 1/3 plus c. If I subtract 1/3 on both sides, I'm going to get c equals 1/6. Now I'm going to take that c value and I'm going to just plug it back in to make my equation. Now, y is not by itself yet. That's going to be my next step, is to get y by itself. So I'm going to have 1/2 y squared equals 1/3 x cubed plus 1/6. Now, in order to get y by itself here, I need to undo the 1/2 and I need to undo the squared. And we're going to do that in 2 separate steps. So step number 1 is I'm going to multiply by 2 on both sides. And the reason I'm going to multiply by 2 is that the opposite of dividing by 2 is just multiplying by 2. So if I multiply by 2 on both sides, the 1/2 and the 2 cancel. I just get y squared equals, now I'm going to multiply each of these by 2. So 2 times 1/3 would be 2/3 x cubed. 2 times 1/6 is 1/3 because 2/6 simplifies to 1/3. Next, I'm going to square root both sides. And the rule for square rooting is that square roots have 2 answers, plus or minus. So I would have plus or minus 2/3 x cubed plus 1/3. Now remember, we're not allowed to keep the plus or the minus in the final answer. So what I'm going to do here is plug in the number 1 from the initial value. I'm taking that x and I'm plugging it in. 1 cubed is 1. 2/3 times 1 is 2/3. 2/3 plus 1/3 is 3/3. So that's really a 1. So we have plus or minus the square root of 1. Now, based on this initial value, we wanted our answer to be -1. So I'm going to keep the negative here. That means my final answer to this problem would be y equals negative square root of 2/3 x cubed plus 1/3. And that would be my final answer. All right, let's try another problem. So this one again has something else that's a little bit algebraic, a little bit tricky that we want to make sure we review. So our initial equation here is dy over dx equals e to the x plus y. And we want to find the particular solution. So one thing I want to point out and make sure you see is that the y is not by itself here. And when y is not by itself, just like when we took the derivative, we had a special strategy. We have a special strategy for doing the antiderivative. So the first thing you need to know is that we can actually separate the x and the y here. Because there's a plus sign in the exponent, this really means e to the x times e to the y. And the reason that that's the case is because when we learned about exponents a long time ago, we said if you have a multiplication problem, you just add the powers. So if we see powers that were added, it must have originally come from a multiplication problem. Now, the reason that that's so important is that until you do that, you really can't separate the x and the y here because they're both part of the same exponent. So instead, once we do that, we can actually separate. I'm going to start by dividing by e to the y on both sides, and that's going to cancel this e to the y. I'm also going to multiply by dx on both sides, and that's going to cancel that dx. So my new and separated equation is going to look like this. I'm going to have, because I divided by e to the y, I'm going to have 1 over e to the y times the dy that was already there. And because I already had an e to the x and now I multiplied by dx, I'm going to have e to the x times dx. Now, before I do the antiderivative here, I always like to rewrite this as e to the negative y. And the reason I like to do that is it helps me to see the powers a little bit better and helps me strategize how I'm going to do the antiderivative. Now, as a reminder, dy and dx mean that this is the derivative equation. So to undo the derivative, we need to do the antiderivative, which means we're really integrating on both sides. One of the reasons that I find it really helpful to rewrite this problem with that negative exponent is it helps to remind me that in order to do this antiderivative, I need to take into consideration chain rule. Because that's a negative y and not just a positive y, I know that I would have done the chain rule when I took the derivative. So to undo that, I'm going to start by dividing by the chain. Now the chain here would just be -1. Now I'm going to do the antiderivative of the outside. The antiderivative of e to the negative y would just be e to the negative y. But since I had to divide by that -1, it would be negative e to the negative y. Equals the antiderivative of e to the x is just e to the x. And then I'm not going to forget to put my plus c, but I'm only going to do that on one side. Now, once I get to here, I'm going to go ahead and find out what c should be. And I'm going to do that using my initial value that I was given here, where x is 0 and y is the negative natural log of 2. So I'm going to go ahead and plug that in. So if I plug in x is 0 and y is the negative natural log of 2, I have negative e to the negative, and now I'm going to plug in negative natural log of 2 equals e to the, I believe it was 0 plus c. Now, e to the 0 is just 1. A negative and a negative work together to make a positive, and e's and natural logs are opposites, so they cancel. So I'm going to have -2, and then if I subtract 1, I get that c is equal to -3. I'm going to take this c and I'm going to plug it back in. So my new equation, and again, y is not by itself yet, but it will be soon, hopefully, is going to be negative e to the negative y equals e to the x minus 3. In order to solve this, I'm going to start by dividing by a -1 on both sides to cancel that negative that is outside of the e to the negative y. When I do that, I'm going to have e to the negative y equals, and I'm going to divide both of these things by -1, so I'm going to have negative e to the x plus 3. Now I'm going to do the natural log of both sides because the natural log is the inverse operation of e. And I'm going to have negative y equals the natural log of negative e to the x plus 3. And then I just need to divide by -1 in order to get the y by itself. So I have y equals the negative natural log of negative e to the x plus 3. And there we go. That's our final answer. We're going to have one more example that we're going to do. And the reason I want to talk about this example is that this is one of those cases, and we talked about this with implicit differentiation as well, where the fact that the y is not alone is sort of hidden in the problem. What I want to point out to you here is that because this equation is dg over dt, in this problem, the letter g is acting like y. Because g is not alone here, it's in the middle of the problem, it tells me that this is a problem where the y essentially is not alone. So the first step of this problem is going to be to separate the x's and y's, or in this case, the g's and the t's. Now, just like I normally move y to the left-hand side, I'm going to move g to the left-hand side. In order to do that, I'm going to start by dividing by g minus 5 squared on both sides. I'm also going to want all the t's, or in this problem, it's kind of like the x's, on the other side. So I'm going to multiply by dt on both sides. Now, in this case, this g minus 5 squared cancels this one. And on the other side, I'm just going to have 1 over g minus 5 squared times the dy that was the dg that was already there. And on the other side, I have the -2 times the dt, which cancels on the left-hand side and is moved to the right-hand side. Now, in order to do the antiderivative here, just like before, I like to rewrite this with a negative exponent. So this guy right here would really be g minus 5 to the -2 power. Again, I want to remind you that having the dg and having the dt tells you that this is the equation of the derivative. So to do the inverse operation and get the original, we need to do the antiderivative, which is the integral on both sides. Now, normally I would say, hey, this is a problem where chain rule might have happened. But the derivative of g would just be 1, and dividing by 1 doesn't change anything. So I can just do the antiderivative of the outside, and that's all I really have to do. I would add 1 to the power, so the new power would be negative 1, and divide by the new power, so negative 1, and leave the inside alone, so g minus 5. On the right-hand side, I'm going to have the antiderivative of negative 2, which would just be negative 2t, plus I'm going to put my c on one side and one side only. Now I'm going to take a second and take that initial value that I was given in the instructions, which is that g of 5 is equal to 4, and I'm going to go ahead and plug that in. So when x is 5, y is 4. In this case, that would be like g and t. So in this case, and I'll label this so that everyone can see it. The input here is t and the output here is g. So I'm going to go ahead and plug that in. When I plug that in, I get negative 1 times 4. I'm pretty sure it's 4, yeah. 4 minus 5 to the negative 1 power equals negative 2 times 5 plus c. Now 4 minus 5 is negative 1. So I have negative 1 times negative 1 to the negative 1 power. It's a lot of negative 1s. And then negative 10 plus c. A negative power really just means make that in the denominator. So I have negative 1 over negative 1 equals 10, negative 10. This is really 1. So if I add 10 on both sides, I get that c is 11. Now I'm going to go ahead and take that c and just plug it in. So my new equation, and again, the g is not alone, but it will be by the end of the problem. We're going to have negative 1 parentheses g minus 5 to the negative 1 equals negative 2t plus 11. Now I want to get g by itself. So I'm going to go ahead and start by dividing by negative 1 on both sides. So I'm going to have g minus 5 to the negative 1 power equals, I'm going to divide both of these by negative 1, so I'm going to have 2t minus 11. Now, a negative 1 power really means division. So this really means 1 over g minus 5 equals 2t minus 11. There's a lot of different ways to do this, but what I like to do is, if one of the things I'm trying to solve for is in a denominator, I like to make it fractions on both sides so that I can just use cross multiplication. So 1 times 1 is 1. And then I'm going to have g minus 5 times 2t minus 11. In order to get g by itself, I'm going to divide by 2t minus 11. And that's going to give me 1 over 2t minus 11 equals g minus 5. And then I'm just going to add 5 on both sides. So I'm going to have g of t equals 1 over 2t minus 11 plus 5. And that would be my final answer. All right, thank you guys so much for sticking it out through kind of a long video. I know that this was a lot today, but a lot of it is also just a review of algebra skills, which I know is a little bit challenging. It's been a long time since we solved a lot of equations like this. So I will see you soon for some practice, and thank you guys so much for watching.